In this lesson, we'll define limits at infinity and explain how they relate to graphs of functions. So to start with, the definition. When we say a limit at infinity, we mean the x values in f are approaching either negative or positive infinity. These limits may or may not exist, but if they do exist, and let's say is equal to L, it'll turn out that y is equal to L is a horizontal asymptote of your function. So there's two different limits because you can either go to positive or negative infinity. And in fact, both can exist, and they don't have to be equal. They could be two different limits. And this would mean there are two different horizontal asymptotes on your function if this occurs. Let's see how this idea works by looking at example 1. Here we have a graph of f of x, which I put here as 1 over x, and I'd like to find all asymptotes of this function just by using the graph. Well, to start with, there's a vertical asymptote at x is equal to 0, and I can abbreviate this VA. The reason this happens in this function is because it's a rational function, and 0 makes the denominator and only the denominator 0. So we can use that fact instead of using limits. So you can actually see it in the graph itself. X is equal to 0 is a vertical line that the graph approaches. Now, by looking at the graph, are there any other asymptotes? And the answer is yes. There are also horizontal asymptotes. And I'll abbreviate this HA. And actually, there's only one horizontal asymptote. If you look at the graph, it looks like the line y is equal to 0, which is the x-axis, is a horizontal line that the graph 1 over x approaches. So what's the horizontal asymptote? It is, in fact, y is equal to 0. Now, how does this relate to limits at infinity? Graphically, if you look at the limit as x approaches positive infinity of f of x, I'll write that down here. So that's the limit as x approaches positive infinity of really 1 over x. What's going on in the function? We're heading in this direction towards positive infinity, and 1 over x, the y values on the graph, are always getting closer and closer to 0. And we can think of 0 as the endpoint. So graphically, I'll just say it's 0. I mean, really, I kind of think of this as we have a fraction that is 1 over something really big. So we're putting very large numbers into the denominator. If you take a number 1 and divide it by something that's huge, the result is going to be small. And in fact, so small that it is approaching 0, and 0 is the limit. Now, is the same thing true as we approach negative infinity for 1 over x? And the answer is also, yeah. If you go in this direction towards negative infinity, the y values on the graph are negative, but they're getting smaller and smaller and smaller, and as a limit, we would say that is going to 0. So again, I'm still using this. Well, if we have something like 1 over a big number, and even if the number is negative, if you think about the absolute value of the number, it still is going to be something that is small in absolute value. So it's like 1 over something big is small. So these two statements are true. This is in no way a proof, but I can see it graphically. So that is enough to justify these two limits. Next, we'll expand this by stating a fact, and we can use this to help us solve more complex limits at infinity. Here's a fact that we will use in solving several limits in this lesson. That is, if a is any constant, some number like 5 or negative 4 or something like that, and r is some positive number that just has to be greater than 0, if you look at a over x to the power of r, if you approach either positive or negative infinity, the result is going to be 0 in the limit. And the idea behind this is, okay, you have a number which is fixed, but you're dividing it by something that is getting very, very big. And the result is going to be very, very small. So I'm looking at this as we have a number over something that is very large, in fact, getting larger and larger and larger. It'll always be that the result is smaller and smaller and smaller, eventually going to 0. So not a proof, but just something conceptually that you could think of off of a graph. I'd like to use this fact to quickly compute these 3 limits. So, for example, what is the limit as x approaches infinity of 5 over x squared. So here a is 5 and r is equal to 2. Is this limit 0? Well, according to this fact, yes. This is a lot like the graph of 1 over x. But actually, since you're squaring the denominator and you're heading towards infinity, this is getting even larger than 1 over x is equal to. And it must be, if you looked at a graph, y equals 0 would be a horizontal asymptote. So no more justification is needed. This limit must be 0. It's something that is a number over something that is becoming very large, and the result is going to be very small. What about for part B? The difference here is we're going towards negative infinity. Here a is negative 4.1, and r is 39. Well, this x to the 39 is going to be really huge, like way larger than this. So it's still something over a big number, meaning the result will be small. So this is also 0. And lastly, what is the limit as x approaches negative infinity of this expression? Well, it turns out this is not defined. So I noticed up here I put, when defined, we can apply this fact. Why is this not defined? Well, you cannot put negative numbers into the square root. So we can't actually use this to say the limit is 0. But just for another example, what about the limit as x approaches positive infinity of 17 over the square root of x? Is that limit 0? The answer is yes. This thing is actually defined because you are allowed to put positive numbers into the square roots. It might help to write this as the limit as x approaches infinity of 17 over x to the 1/2 power. Here r is equal to 1/2. That's a positive number. This fraction is a number over something that's getting bigger, and that means the result is going to be very small. And as a limit, we can say it in fact does equal 0. So this one, it wasn't defined. But if we switch it to positive infinity, well, now it is. Okay, so in example 3, we're going to compute two limits, and these are already looking much more complicated than the ones in the previous slides. Let's start with part A. This is the limit at infinity, meaning x is approaching positive infinity, of 9x squared minus x plus 5 divided by 2x squared plus 5x minus 3. Ideally, we would like to use the fact that I stated in the previous slide. That is, you want to have things that are of the form a over x to a power. And the reason is, as x approaches infinity, you can say that something that looks like this must go to 0. And so far, nothing in this really looks exactly like this. But there is a trick that you can use so you can put things into this expression that look more like this. And that trick is to divide each term by the x with the largest exponent in the denominator. And this will work really well for these types of expressions with fractions. If you look here, the largest x in the denominator is this x squared, so x to the second power. I'm going to divide each term by x squared, and that is equivalent to multiplying the top and bottom by 1 over x squared, which means we're not changing the value of the limit, but we are writing it in a different way. This will look like the limit as x approaches infinity of, that's be kind of a mess, but it's 9x squared over x squared minus x over x squared plus 5 over x squared, all divided by 2x squared over x squared plus 5x over x squared minus 3 over x squared. This limit and this limit are equivalent because this expression and this expression are equivalent. But this one we can simplify. I can cancel an x squared over x squared. X over x squared is a 1 over x, and so on. So I'm going to rewrite this. This is the limit as x approaches infinity of, so that's 9 minus 1 over x minus 5 over x squared, all divided by 2 plus 5 over x minus 3 over x squared. So this and this are equivalent. But if you notice, These terms with the x's all resemble this. It's a number over x to a positive power. Since x is going to infinity, nothing happens to 9, nothing happens to 2, but this goes to 0, this goes to 0, this goes to 0, and this goes to 0. You can actually write this thing as, the limit is 9 minus 0 over 2 plus 0 minus 0. And that is 9 halves. This limit is 9 halves because this, and this, according to this fact, are 0. Now let's try that here, where, okay, we have x plus 3 divided by x cubed minus 3x plus 1. And I'm still going to use this fact. That is, I'm going to divide each term by the x with the largest exponent in the denominator, which is x cubed. This is the limit as x approaches infinity of, that's x over x cubed plus 3 over x cubed divided by x cubed over x cubed minus 3x over x cubed plus 1 over x cubed. I have to simplify this. If I want to apply this fact, I can't here because I don't have a constant over an x. I have an x over an x. But this is, not too bad to simplify. This is the limit as x goes to infinity of 1 over x squared plus 3 over x cubed all over 1 minus 3 over x squared plus 1 over x cubed. And written this way, this goes to 0, this goes to 0, this goes to 0, and so does this, all by this fact. And therefore, the limit is, well, in the numerator, we have 0 plus 0 over 1 minus 0 plus 0, which is 0 over 1, which is actually just 0. These are the answers for these two problems. This one was 9 halves. This one was 0. And what does this mean about this function and this function? Y equals 9 halves is a horizontal asymptote of this equation, and y is equal to 0 is a horizontal asymptote of this equation. In example 4, we're going to consider this limit at infinity. And the difference is now I'm putting a square root into the numerator. Something to point out that is important for this problem is, if you see a square root of x squared, what does that simplify to? And it's very tempting to, when you see this, simply write x. And technically that is not true. In fact, it sometimes is x, which you could put positive x, but other times it's negative x. And you have to know which one to use. And if x is positive, then you would use the positive x. But if x is negative, then you'd use negative x. So this is going to show up in our expression. And we have to be careful. We have to use either a positive or a negative x. And it will depend on these two cases here. This is how I'm going to approach solving this limit. I'd like to divide the top and bottom by the x with the largest exponent in the denominator, which is x to the first. But I see there's an x squared in the top, and I know if you take a square root of x squared, it should reduce down to an x to the first. So my first step is to somehow factor this x squared out of the square root. The way I like to do that is as follows. I'm leaving the denominator alone, but before I even take the square root, I'm going to factor x squared from both terms. What does that become? Well, there has to be a 9 here because if you take x squared and multiply back to 9, it's got to take you to 9x squared. But then we'll have plus, and then what would go here? Well, you want something so that when you multiply x squared to it, it gives you 1. And that means I'll use 1 over x squared. And the reason is when this gets multiplied here, they cancel and only 1 is left over. This is helpful because, hey, we have a 1 over x to a power. And at infinity, I know something like this goes to 0. So it's like we're going in a good direction. Now, there's a property for square roots that works for products, but not for sums. You're allowed to split the square root across two products. So that is, this is the limit. as x approaches infinity of the square root of x squared times the square root of 9 plus 1 over x squared. And this is still divided by x plus 2. You are not allowed to, in a sum, take the square root of the first and the square root of the second. That is false. I'm allowed to do this because here I have a product of two things. Now, what is the square root of x squared? It's either positive or negative x. In this example, it's going to be positive x. So I'm going to place that. So this is the limit as x goes to infinity of positive x. Why is it positive and not negative? And the reason is we're approaching positive infinity. We're only ever putting positive numbers in place of x. And that means we would never encounter a negative value for x, meaning we don't need negative x as our answer. So from here to here, the reason it was positive infinity is because we were approaching positive x values. I'm now going to divide this term by x, this term by x. This whole thing is one giant term, and I'll just simply divide this part by x. This is the limit as x approaches infinity of, so in the denominator we have x over x, we have 2 over x, and then we have x over x times the square root of 9 plus x squared. You do not also have to divide this thing by x squared. Again, this is one gigantic term. You only have to divide it by x once. It makes sense to divide it here because it'll cancel nicely. What does this all become? This is the limit as x goes to infinity of, well, this x over x is 1. I'm not even going to write it. And in the denominator, x over x is 1, and then we have 2 over x, which doesn't simplify. We are now able to take the limit. And the reason is 9 stays 9. The square root doesn't go anywhere. This one stays 1. But this is 0, and this is 0. So by evaluating the limit, we get root 9 plus 0 over 1 plus 0, which is the square root of 9 over 1, which is simply 3. And that is the answer to this problem. You might want to consider for this, what happens as x approaches negative infinity? Will the answer also be 3? And the answer to that is no. The answer is negative 3. And the reason is, if you approach negative infinity, you'd have to have a negative here in front of the x. And that negative will never go away, meaning negative 3 is your answer. I'd like to do one more example where we compute another limit at infinity, but here we're going to use e to the power of t instead of a polynomial. Before figuring this out, I'd like to determine, by using this graph, what is the limit as we approach e to the t as x goes to negative infinity, and also what happens as we approach positive infinity. And I want to answer this just directly by looking at the graph of e to the power of t. Let's start with this one. All right, so what is the limit as t approaches infinity of e to the t? Well, if you look at the graph and you're going in this direction, it never will level off. In fact, it's getting bigger and bigger and bigger. I'll quickly state that the answer is infinity, or if you'd like, you could say positive infinity. So this technically does not exist. Now, the limit as we approach negative infinity, this limit does exist. It's not positive or negative infinity. In fact, it's 0. The graph is approaching y is equal to 0, and y equals 0 is a horizontal asymptote of this function. So just by looking at the graph, this is 0. How can these facts help us solve this limit? So here we have 3 minus e to the t over 4e to the t plus 2. I'm actually going to use the same trick that we did in the previous problems. I'm going to locate the variable in the denominator that has the largest exponent. And here, that is actually e to the t. So the trick will be the same. I will take my limit as we approach infinity, and I'm going to divide every single term by e to the t. And now I'll simplify. This is the limit as t approaches infinity of, well, 3 over e to the t does not simplify, but e to the t over e to the t does. It's 1. 4e to the t over e to the t is just 4, and we have plus 2 over e to the t. And I claim at this point we can just state what the limit is equal to. Why is this? As t approaches infinity, using this fact here, the denominator is going to infinity. And the same thing is true for this one. This means if you have the limit as t approaches infinity of something like a number over e to the t, this is 0. And it's because you have a number over something that is very big, meaning the result is very small. So for the same reason, we can say, well, this is 0, and 1 and 4 don't change. So we get 0 minus 1 over 4 minus 0, and that answer is negative 1/4. That is the answer to this limit at infinity. I think I'll include one more limit here, just because it's worth considering, and it'll be very simple to compute. What is the limit as t approaches negative infinity of this same function, 3 minus e to the t over 4e to the t plus 2? The reason this is very easy to solve is you don't have to use any trick to get your answer. As we approach negative infinity in e to the t, it actually just equals 0 itself, meaning for here, you can actually just put this as 0 and this as 0, because I know what happens to these things as t approaches negative infinity. This turns into a very simple limit. It's 3 minus 0 over 4 times 0 plus 2, which is 3 over 2, which is 3/2. What does that mean about the function 3 minus e to the t divided by 4 e to the t plus 2? There are 2 horizontal asymptotes on 3 minus e to the t over 4 e to the t plus 2. They are y is equal to negative 1/4 and y is equal to 3/2. And that is it for this example.